Okay, so welcome to lecture 2. Today we're going to be talking about the foundations for learning and how to optimize networks. And in particular, we're going to be asking about, number one, what is machine learning? Number two, how do we define traditional neural networks before we dive into convolutional neural networks and recurrent neural networks and some of the modern architectures in the next couple of lectures? And how do we use gradients for optimization? And how do we do gradient descent? And how can we train neural networks across many layers and specifically deep neural networks? And what kind of performance metrics should we use? How can we manage gradient optimization? And most importantly, how do we regularize a model? Because, you know, back in the 60s, the challenge was, how do we add complexity? How do we add parameters to our models? The problem that we have today is, how do we limit the parameters? How do we make sure that the model doesn't just simply remember every single example that it's ever seen and have this enormous model capacity? So we're going to talk about regularization for controlling parameters and model complexity. So what is machine learning? So all of us have some kind of intuitive notion of what machine learning is. Let's define it formally. So, you know, there's been many definitions proposed. So learning is the process of converting experience into expertise or knowledge. Machine learning can be broadly defined as computational methods using, again, experience to improve performance or to make accurate predictions. So there's an aspect of, you know, using your past experience to now become better at some kind of future goal. Murphy, 2012, the goal of machine learning is to develop methods that can automatically detect patterns in data, and then to use the uncovered patterns to predict future data or other outcomes of interest. And that goes back to many of your comments when you were saying, hey, there's patterns in biological data. That's why machine learning makes a lot of sense. But once more focused on the concept of using these patterns to then carry out a predictive task. And another definition is to state the learning task as, given the value of an input vector, make it a good prediction of the output y, denoted by some y hat. So we're going to define in this class machine learning as learning from an experience with respect to some class of tasks such that the performance measure P improves with more experience. And that's the definition proposed by Mitchell in 97. So if the performance at a particular task as measured by P improves with experience E, then there's learning involved. And that's the concept of machine learning. So there's always a task, there's always a set of data that we're building with, and then there's always some kind of measure of performance. So let's see who's with me so far. Awesome. If there's any questions, please add them to the chat and we will respond to them as they come. Awesome. So, for example, in your first problem set, the experience E, namely the data, the sort of the stuff that the machine learning model is going to be learning from, is going to be a training set of images of handwritten digits with labels. That's going to be your training set. What's going to be your task? The task is going to be to classify future handwritten digits in new images. And that's a test set. That's very different from the training set. So the training set is what you use to fit the model parameters, the model architecture, and so on and so forth. And the test set is sort of when you evaluate how well is the model performing. And again, the challenge is that if you have enormous numbers of parameters, then evaluating your performance in the training set simply means, oh, I remember this image, I've seen it before. Whereas for the test set, it's really about generalization power, and that's going to be key in everything we do. And then the performance measure is what's going to be the percent of test set digits that are correctly classified. Okay. So You don't have to worry about the notation so much, but just for consistency, we're going to be talking about scalars. These are sort of one-dimensional objects, vectors, which are sort of two-dimensional objects, matrices, which are sort of, scalars are just one number, vectors are a string of numbers, matrices are a two-dimensional grid of numbers, tensors can be anything. They can be, you know, vectors, scalars, matrices, or higher dimensionality constructs, sets, and we're going to be talking about the input space, individual examples of such objects. A particular example of a data set is going to be using particular indices, and then a particular feature of an example is going to be shown this way. And then we're going to be talking about the label space and the particular label of the example and the, you know, particular predicted label for that particular example. That's the y hat. So our inputs are going to be x's and our predictions or our outputs are going to be y's. And that's how we're going to be denoting the different dimensionalities of them. So again, we're going to be talking about an input x and an output y and a function that translates x into y. So basically what our neural networks are going to be doing, or just any machine learning technique is going to be doing in the class, is going to be evaluating some features extracted from you know, the input data, and then using these features to compute an output result. And most of the time, it's going to be some kind of deep neural network that has transformations of these data, usually non-linear transformations, which is where the whole power of deep learning comes from. And all of these sort of neural networks, the fact that they have non-linearities means that they can approximate an immense number of functions, whereas if they were all linear, they would only approximate linear functions. So our input is going to be particular features, or in statistics, these are known as predictors or independent variables or regressors. So again, you know, just even linear regression can be thought of as a machine learning task where you have a set of input points X, you're sort of predicting a set of outputs. And the way that you're doing these predictions is by minimizing, I don't know, least squared errors, for example, and so on and so forth. And then again, these are going to be the input variables and the covariates, and the outputs, we're going to be talking about them as labels in machine learning, but they can be thought of as responses in statistics or dependent variables from the independent variables. So these are the inputs which are independent, and then the dependent variables are the ones that are derived from the independent variables that are the dependent variables. Or the regressants in regression analysis.
Hello, Dad, there's a visit.
Λοιπόν, παιδιά, ο μπαμπάς αυτή τη στιγμή για μία μισή ώρα έχει πάρα πολλή δουλειά. Εντάξει, πηγαίνετε όλοι πάνω. So, school vacation week, yay. So we're, you know, if you guys want to stop and play castles, I have another Zoom session up there. So for our three little ones. Okay, so our training set is going to be, you know, the set of input parameters and input, basically, so our training set is going to contain a set of known x's for which the y's are known. And then our test set is going to be an independent set of x's for which the y's are also known. And then our goal will be ultimately to let this out in the real world when we're not going to know the y's. So we're going to have a collection of features and associated labels. And the training is going to be to use that training set to learn the functional relationship between x and y, how to transform x's into y's. Everybody with me so far? Lovely. Good. So now our terminology is that the function is going to be taking in the input and some parameters and then computing the output. Okay, so our input is going to be a set of binary images, which are going to be 28 by 28. Our output is going to be which image is this? Is this a 1, 2, 3, 4, all the way to 10? And the output is going to be zeros everywhere except for the digit that we're predicting. And then our weight vectors, which are going to be the parameters of our model, is going to be sort of the corresponding weight for all of those, and some bias or some sort of basic sort of offset for any kind of predictor. This is called a bias because in absence of any data, this is just the offset from the zero that you're predicting. So this is just a basic, output of a linear function when there is no x's. And then we're going to be optimizing all of this. So we're going to be using weights and biases, which are going to be these intercepts, and then particular coefficients, which are going to be telling us about how we're going to be combining all of the values of all of the pixels, and then parameters. So that function, that transformation function, can be thought of as the model of the world. So in our first lecture, we were talking about how there's observables in the world, and then there's inferences that we're making from the world. Inferences are our models, our hypotheses, or in machine learning terms, they can be our classifiers, these functions that basically, well, it's a 1 or it's a 2. But these classifiers are effectively making hypotheses, making inferences about the world, okay? And those inferences are sometimes going to be categorical. This is what digit I believe it is. And remember, when we're talking about the weather, when you're observing a cloud and yet then you're inferring that it's winter, for example. So this is going to be the particular types of inferences that you're making. So you are abstracting away from the low level data that you're observing in the world into a high level concept of what is my current hypothesis, my current model, or my current class that I'm predicting from the world. Just 1 second. So we're going to be looking at both discriminative models, which are only going to care about whether something is, a cat or a person, for example. Be careful about your zoom filters here. Or a generative model, which actually models the joint distribution, okay? And that, we again talked about it in lecture 1, the concept of a parameterized model, which actually tries to capture the distribution of weather patterns in the world, or in a self-driving car, you're trying to model the distribution of all objects, whether this is a tree or a person or a bicycle or a truck and so on and so forth, as opposed to a discriminative model that is simply trying to decide, do I stop, do I go, do I turn right, or do I go turn left? So you're only, sort of choosing between, say, 4 actions, or you're trying to build a complete model of the world upon which you then take those actions, okay? Let's see, who's with me so far? And let me look at the chat to see if there's questions. Okay. Okay, cool. Yeah, so Mirna, these are all great questions, and we're going to be talking about those in much more detail. Okay, lovely. So, okay, so, again, all of this is going to be super concrete as you guys start working on your first problem set. So remember, PSET 0 is due on Monday, and PSET 0 is just setting up your environment. And then after that, PSET 1 doesn't yet tackle biology. PSET 1 is going to be all about this Institute of Standards, MNIST data set, which is these handwritten characters. So please work on setting up your environment this week. And then starting next week, you can start working on this problem set. And then all of these are very concrete as you start doing that. Okay, so we're going to have an input space, and then after rescaling, after flattening this vector, we're going to have just a string of 1s and 0s, and then encoding the label space in this binary vector with something known as one-hot encoded, which basically means that out of a vector, you're choosing the class by setting just one of these variables as 1, and that becomes a hot variable. That's the variable you choose. Okay. All right, so now machine learning does not need to simply be classification. So basically in our first problem set, we're gonna be choosing between 10 different classes of characters from 0 to 9, but classification is just one of many, many different tasks of machine learning. Another very common task is gonna be regression. So you're not trying to say, is this, a particular, is this a cat or a person? you're trying to say what is the actual value of a particular function. And again, linear regression is extremely common, quadratic and higher dimensional regression. And then there are many transformations that you can make on the data that allows you to apply either linear classifiers or linear regression or other sort of simple models based on a transformed data set. And that's something that, again, we're going to be seeing throughout the class. And of course, there's a whole other class where you don't have any kind of labels. So with both classification with regression, we know what the output should be. We have a Y, which can be either the class of, blue or red, or the value of the output function. Whereas for unsupervised learning, we're just given a lot of data and we're looking for patterns in that data. That's still learning because you're learning a model. For example, you might infer that there's a mixture of Gaussians and that this distribution comes from flipping a coin for blue or orange. And then if you flip blue, you then sample from the blue distribution, which might be some kind of Gaussian, or in this here might be, another sort of, I don't know, gamma distribution or some other distribution that you're sampling the points from. So even if you don't have a predictive task, even if you don't have an output variable that you're trying to predict, the input data in some X space, which is a multidimensional space, can still give you enough information to learn patterns, okay? So we're gonna be talking about supervised or semi-supervised learning, and semi-supervised means when you have both the ability to learn structure, and then you have labels for a subset of the points, and then by learning the structure and having labels for a subset, you can infer a learning function, a categorization, or a regression from that. There's also models of learning where you're not given all of the training answers from the beginning, where you're, for example, given only an answer every so often. So reinforcement learning is one type of this partial input from the world, partial feedback, where you're sort of learning how to navigate, and only every now and then you get some feedback about the actions that you've been taking. So you can distinguish these different functions based on the Y function that you have. Basically, how much do we know about the output? And this is a not equal sign. If it's not equal, if it's not empty, then it's supervised or semi-supervised. If your output is a set of real numbers, then you can think of this as regression. For multivariate regression, it's a multidimensional set of numbers. And then a binary classification is when you have either 0 or 1 or multiple classes, or a multi-class classification, where you can sort of, again, one hot integer encode these, or a multi-label classification, where you're trying to predict multiple labels for each value. For example, it's a cat that's, I don't know, happy, and it's a person that's sad, and so forth. And then unsupervised learning is when you don't have any output variable, okay? So again, your Y is gonna be, the multi-class classification for problem set 1, and we're gonna be using softmax regression, which is also known as multinomial logistic regression, as a multi-class classification method. So and we're going to get a little more into the detail about that, but instead of using linear regression, you're using a nonlinear function, which can be a sigmoid or a softmax function or a logistic regression function, and so on and so forth. All right, so let's talk about that objective function. So the objective function is going to be the function that you're optimizing when training your machine learning models. And it's usually in the form of one combination of either a loss function or a cost function or an error function. So an error function doesn't penalize errors differently. It just simply says this is correct or this is not correct. A cost function can basically have a cost associated with either false positives or false negatives or how far off you are, and so on and so forth. And a loss function is the difference between what you're trying to predict and what you're actually predicting. So it can actually be a quantification of how wrong you are for every one of those. So for classification, you can think of 0-1 loss, which is either you got it right or you didn't, or cross entropy loss, which is what is the sort of joint information between what you're predicting and what you should be predicting, or a hinge loss, which is variation thereof. For regression, we're going to be talking about mean squared error or mean absolute error. So this is the L1 norm or the L2 norm. And these are, very frequently referred to as L1 and L2. And we're going to see this in regularization as well. So we're going to be talking about L1 regularization, L2 regularization, which is basically simply means linear or quadratic. Okay. So what is this? This is basically asking how far off am I from where I'm trying to predict? And I'm either using the absolute value by which I'm off, and that's a linear penalty, or I'm using the square of the value, which, kind of naturally makes this symmetric, whether you're up or down, but it also penalizes far outliers much more than the nearby ones because of this quadratic increase in the penalty the further you go. And we can have hybrids between them. And even for regularization, we can have hybrids that combine both L1 and L2 norm regularizations. We can also have probabilistic inferences that are basically saying how different are the distributions of functions between the y's that I'm observing and the y's that I'm predicting. Okay. And then we're going to be talking about a likelihood function and a posterior probability, a posterior distribution, which is going to be basically telling us what is the maximum likelihood estimator if I don't have any prior expectation for what the data should look like based on just the data. Or if I have a prior expectation, then what is my posterior probability or the maximum a posteriori or the map estimator of either the value or the class and so on and so forth. So basically this is going to be using a Bayesian setting, as we talked about in the first lecture, where we're using not just the evidence that we're observing, but also the likelihood of that, which is the reversing of the errors that we talked about last time, but also the prior for every one of the classes. And then we're going to be having some constraints on the parameters, because we don't want to assign too much weight on any one on any one input value, because then it's much more likely to overfit and it's much less likely to generalize. So we're going to be penalizing for the total sum of all of our parameters, either linearly or quadratically. Linearly in the absolute value or quadratically, which again takes care of the absolute. And then we're going to be talking about this max norm, which is going to be evaluating that. So for classification, we're going to be talking about 0-1 loss, which is simply saying how often am I predicting the wrong class from the class that I should be predicting. And this is just a sum of the number of errors. And the binary cross entropy loss is actually going to be looking at the Bernoulli distribution of that discrepancy. So basically, what is the probability of generating each of these values and how far off are these values compared to their probability? So this is simply weighing everything by the probability of that occurrence. And this binary cross entropy loss is simply the information-based value for this, which is simply, the corresponding equation that matches this entropy. Okay, so this is just the cross entropy between those two values according to the distributions given by these Bernoulli distributions, which are, a probabilistic event that generates ones and zeros. So we're going to be talking about loss functions for classification, which is, again, this binary cross entropy loss, and then looking at what are the y's, the labels, what are the estimations of those y's in logistic regression or this, other kinds of nonlinear classifiers for our problem set. And then what is the maximum estimate based on simply a binarization of that output. And then the corresponding loss, but also the cross entropy, which captures a lot more about how close our predictor is by directly using the values rather than the binarized versions of those values. And that's sort of where the cross entropy information is actually helpful. So the categorical cross entropy loss is going to be using this particular information-based approach, but we can also use softmax, which is going to be looking at this sigmoid function that maps the space into a 0, 1 output using this particular formula, which we're going to be seeing throughout the class. So again, the output is 1 only if it belongs to the class, and otherwise it's 0. And then the probabilistic interpretation is that the likelihood is defined according to the distribution of elements in those categories. So again, the structure of the problem set is that we're going to have a set of input data, a set of weights, and this bias term, the offset, that we're going to be combining into a predictor, and then the actual output and a loss function. And we're going to be building the optimizer based on the discrepancy between these weights feeding into this loss function. So that is going to be used for actually training the weights of our prediction. And the way that we're going to be doing this is by evaluating either the mean squared error or the mean absolute error from these data sets. And then the mean squared error, again, penalizes the far off errors, the bigger errors by a lot more, and the smaller errors by less. So up until now, we've only been talking about every penalty of every error being the same, but we can also talk about risk, which is the loss associated with how much a particular prediction will cost us. For example, saying that someone doesn't have the virus and then letting them out in the real world in a big party might be much more detrimental than falsely saying that the person has the virus and having them miss out on a party, but then the cost to society is smaller. So we can use risk instead of just loss, and we can use this risk associated with particular hypotheses of the distributions of those values in our world. So we can talk about this distribution and how it impacts this risk, not just a binary loss for this. And we're going to be trying to optimize the objective function, which is going to be getting close to that output. And that objective function can be, a loss function, a cost function, a risk function, and so on and so forth, or the mutual cross entropy. And we're going to be initializing the model parameters, and then we're going to be taking the derivatives of our function to basically of our output with respect to each of the weights. So we're going to be asking, how much can I vary my parameters to move towards a global cost minimum? And we're going to be doing a gradient descent according to that minimum. So in pset1, we're going to be using stochastic gradient descent, where at every step, we're going to be randomly sampling a mini batch, not all of the data, but a small subset of the data from the training data, and updating the parameters using the gradients that we're calculating specifically from that mini batch. So that basically means that as I'm going through the data, at every iteration, instead of trying to make an update that minimizes everything at once, I'm going to be minimizing with respect to different subsets of the data each time, and the gradient is going to be moving sort of slightly in a slightly different direction each time, but ultimately using all of the data in the minimizations and then taking the derivatives with respect to each of the parameters, each of the weights. So in order to ask, how do I update my weights at the next time point at t based on the delta that I'm taking from t-1. So these are the weights at the previous time point. I'm updating each weight at the next time point t by taking the derivative of the loss function relative to each of the weights that I'm optimizing. So then the objective function is that loss function, which is evaluating over all of the training data. Okay, so let's see who's with me so far. Cool. So most people are still mostly with me. All right, so now let's talk about training and evaluation. So we're going to be using both a training set and a testing set. So why are these helpful? Because as I train the model more and more using this gradient descent that I'm going to be telling you a lot more about very shortly, I can minimize the loss further and further and further. But what's really interesting is that if I keep a separate validation set, a validation set that's completely separate from our training set, what's really fantastic and super interesting is that as I get better at the training set, I'm also magically getting better at the validation set. That basically means that there's truly a function that maps X to Y, and I'm truly learning that function using a subset of the data. But then again, something extremely important happens after a certain period, after a certain amount of training, which is that my error, my loss function on the validation set starts going up. So what's happening here? What's happening is overfitting. So again, underfitting basically means that there's a function to be fit. And if I'm in this regime, in the early epochs of training, then I still haven't truly learned that function. I still haven't used the full power of my model to approximate that function. But after a while, I'm approximating that function on the training set a little too well, which basically means that I'm starting to actually perform worse on a future validation set where it might not have the particularities of my input data. For example, I might, I don't know, in classifying pictures of cats versus humans, I might realize that all the cats are wearing, I don't know, pink pajamas in all of the pictures. And therefore, as I train further, instead of having the ears and the whiskers, etc., I'm sort of catching the shadow of the pink pajamas on the face of the cat. And that's only there in my training set. It's not there in my validation set. So I'm not truly learning something true about that function. I might learn that, I don't know, all of the pictures were camera, or something that's not quite relevant to future images. So again, we're going to be splitting the data into, number one, a training set, which are going to be used for that training. But then here's the challenge. If you basically say, oh, okay, great, well, I'm going to stop the learning process when my error in this held out set starts increasing. So that basically means that I'll stop exactly there. But maybe if I have a separate data set, it could have just been, slightly off from that other separate data set. So the way to combat that is to basically say, well, great, now I've minimized my loss function based on an independent data set, but I don't truly know the performance because I've kind of overfit the number of epochs that make the validation set loss minimal. But I don't really know whether that minimal loss will be the loss that I would expect for another random sample of images or another sample of, evaluation objects. So the key idea here is that both the training set and the validation set are samples from an underlying distribution that has all kinds of biases. So therefore, if I'm able to stop by observing what actually minimizes my loss, I don't truly know the true generalization power. That's why we typically split the data into a validation set that is used to tune how long should we train, or to tune hyperparameters. For example, how many layers should my neural network have? What kind of convolutional filter should I use, and so on and so forth. So all of that can be used for evaluation of the expected generalization power, and that's what the validation set is for. And then we truly test the performance of a fully trained model on an independent test set. So a set of examples that's only used to assess the performance of a fully trained model. And after that assessing test of the performance, the model cannot be tuned any further. You can't say, well, I'm not doing so great, let me train a little longer and then see how I do, because then you'll need to use a whole other test set that you haven't seen before. All right, so let's see who's with me so far. Lovely. Good. Okay. And the next question is, let's see, share results, stop share results. Who feels that they've learned something? Awesome. Good. This is very helpful. So 35, 26, 26, 13, 0. This is great. Okay. So how do we evaluate accuracy? How do we know whether we're doing well or not? So yes, this is where we evaluate the accuracy, but how do we actually evaluate the accuracy? And there's many ways of doing that. We can look at the true positive power, which is what fraction of our, the true positives and the true negatives. That's sort of the green part is what we want to maximize. And the red part are basically false positives and false negatives. So if you predict that something is positive and it's truly positive, then it's a true positive. If you predict positive, but it's actually negative, then it's a false positive. False negatives when you predict negative, but it was truly positive, and a true negative when you predict negative, but it was truly negative. So then you can evaluate the accuracy, the precision, the specificity, and then the recall according to these fractions. So the specificity is how many true negatives do I have out of all of how many negatives have I predicted correctly? The specificity, that's the specificity. The sensitivity is how many positives have I predicted correctly? So among the positive ones, how many did I predict correctly? And specificity is among the negative ones, how many did I predict correctly? The precision and the accuracy is again among all of the true positives, among all of the predicted positives, how many were truly positives, and then the accuracy is among the entire population, what is the total sum of both true positives and true negatives. And the F1 score combines both the recall and the precision, and these vary greatly based on the balance of your data set. So if your data set is greatly imbalanced, then it's going to be much easier to get, say, great sensitivity, but at the cost of, specificity and so on and so forth. So again, we're going to be talking about the proportion of true predictions in this particular way. Okay, so these are all of the predictions that I'm making, and this is the true positives and the true negatives. And then the receiver operating characteristic, again, which comes from the transmission of different channels during the war and in sort of communication, is basically saying, as I tune the threshold of my classifier to be, very strict or very loose. So as I adjust the sensitivity and the specificity, along which curve do I function? And you can get better and better performance by having, just an overall higher curve of sensitivity specificity trade-off, where a random classifier would have, walk along the diagonal, and a perfect classifier would walk along the axis. And you can measure the overall area under the curve, or the AUC, or the, AUROC, the area under the receiver operating characteristic, to basically say, what's an overall better classifier, even though in specific cases, you might end up with, curves that cross. So in this regime, this classifier is better, whereas in that regime, this other classifier is better. And in this regime here, this classifier is better, and so on and so forth. So they don't necessarily need to be monotonically ordered, where this one is always better than the other one. These curves could actually be crossing. Okay. So again, because the receiver operating characteristic is actually expecting the true positives and the false, positives and the negatives to be balanced in your data set, there are other curves that are more well suited when the data sets are imbalanced. For example, the precision recall curve, which is looking at precision versus recall, is, better able to capture that for very unbalanced data sets. It's able to do this. And again, these are complementary curves. They capture different aspects. So you could also, in a regression setting where you're actually not classifying examples, but you're predicting the score for an example, you could say, well, what is the correlation between the values I'm actually predicting and the values that I should be predicting, okay? And if you're predicting exactly the right value, then the correlation is 1. If you're predicting, completely randomly, the correlation is 0. If it's -1, then you're in great shape, just reverse your predictor. But usually if you're in this gray zone, then you can probably do a lot better. The challenge, of course, with correlation and Pearson correlation is that even though all of these curves have correlation of exactly 1 or -1, which is great, these curves here, which clearly have a lot of information content, are still showing correlation exactly 0. So because of the way that it is defined, of x minus the mean divided by how many x's there are times etc., then all of these are in fact showing 0 correlation. So there's other metrics for evaluating regression predictors. For example, Spearman rank correlation is not caring about the specific value of the data, but simply the order of the data. And for ties, you can assign some fractional rank based on the average rank in some ascending order. So you can basically say, am I predicting the same rank of the data, even though I don't care about the specific values? And that can be very helpful for, huge outliers or for data that is just not distributed in, typical ways. And here the Spearman correlation is 1 because I can predict all of the correct ranks of all of the data, even though the Pearson correlation is not 1, okay? So let's see who's with me so far. Beautiful. Okay, so good, 43, 36, 21, 0, 0. So then we're gonna ask, how excited should I be to get an 88% Pearson correlation? Is this great? Is this okay? Is this bad? And that's where correlation significant tests come in. So basically we can say, what is the set of all possible results that I would expect? And with what probability would I expect to see this result? And then the significance is simply going to be how unlikely am I to have seen that value for my correlation or for my agreement or for any kind of other metric of accuracy compared to what I would expect for a, random distribution. So the student's t-distribution is basically giving us that expectation with particular degrees of freedom under the null hypothesis. So basically, if n is the number of observations, then we can basically permute the values and calculate the empirical distribution of null correlations. So if I permute my predictor or if I permute my data, then what is the expected distribution of correlations that I would observe? And then see how far off from that, basically where along this distribution of observations am I? And the helpful thing here is that these distributions are actually quite well characterized. So we can actually use a statistical test to say, am I within some significant p-value? And we can talk about the statistical significance threshold with which we have matched the expected data rather than simply the correlation p-value, okay? And this is for a one-sided test, if I expect it to be, very strong, or, but I want to say, is this higher than I would have expected? Then I only have a one-sided test. But if I say, is it different than what I would have expected? That's when I'm using a two-sided test. It basically says, is it above this threshold or below that threshold? And then the two-sided test basically allocate half the area to each direction And therefore, if you're saying it's 95% confident, then it's 2.5% in each side. So they're more strict than you need to if you're only testing one direction, but they are the appropriate test if you're testing deviations in both directions. So we can basically talk about binomial tests that evaluate the probability that the null model will produce the observed results. So if I have n observations and k results that are classified correctly, then the probability of the classifier making the correct choice at random would be p. And then we can actually calculate the probability that exactly k observations would be classified correctly just by chance, just by the null model. And that's simply choosing k out of n times the probability of choosing one of the k positives times the probability of choosing the n minus k negatives, and that's sort of the exact number of these k observations. But if I want to say, would I expect at least k by chance, then I just simply take the sum of that probability using the all of the values that are k or greater, and then each time doing this. This is sometimes known as the hypergeometric distribution, and this is approximated by a chi-square test with the appropriate number of degrees of freedom. And of course, the more hypotheses you're testing, the more likely you are that one of them will come out to be true. So if you're asking n questions, you need to adjust the probability of the null, because if you're excited if any of the classifications are significant and you have 1,000 possible ways of classifying the data, then one of them is bound to come out as significant with, you know, some probability. So the way that you do that is you can correct for these multiple hypotheses. So you can basically use a very strict Bonferroni correction, which is simply saying, well, I have m hypotheses and every single one of them has some probability of coming up by chance. So then the corrected p-value that I should have should be scaled accordingly. And then for any one observation, I better divide the probability of corrected by the number of expectations of the different hypotheses that I'm testing. You can use less stringent correction. The Benjamini-Hochberg provides such a desired false positive rate or false discovery rate using a more relaxed bound, where if alpha is the desired false discovery rate and m is the number of tests, then you're actually testing these in order of their ascending p-values, and you find the largest k such that the corresponding probability is k over m times your desired false discovery rate. And because you're sorting them, you're allowing for that particular threshold to be tuned according to how many would I expect to be at least that probability or at least that probability, and so on and so forth. And then you're rejecting the hypothesis for all of the remaining hypotheses, but not the ones that were above that particular threshold. So then, you know, you can apply that to sort of adjust your threshold accordingly. Again, there's a very cool website for teaching people that correlation is not causation. And you can really enter any curve and it will basically tell you some value out there that correlates with that curve. So for example, the number of people who died by becoming tangled in their bed sheets correlates very strongly with the total revenue generated by skiing facilities. And again, you know, this is just a complete statistical fluke. So you should be aware that, you know, if with enough data, you can find correlations almost anywhere. And then you should also realize that all of these can have zero correlation and yet be high mutual information. So every one of these shapes has correlations near zero. But again, lack of correlation does not imply lack of relationships, okay? All right, so that's some basic foundational tools for machine learning. So now let's shift to, you know, how do we now apply all of this to neural networks? And specifically, you know what I'm going to do? I'm going to ask everybody to stand up for a stretch break. So everybody, please. Can I ask one of our fearless DAs to coordinate the stretch break? So Jackie, unmute and have people do some stretching exercises for us.
Oh, okay. I don't think I'm super qualified to lead this, but this got to stretch out your back. I think that's important. Sorry, y'all. I'm not qualified for this. I don't know if Tess can help or Jang. This is a good thing. You can't even see me. I have a virtual background. That thing. Thanks for the encouragement.
Yeah, you're doing great, Jackie. We can stretch out the shoulders by like crossing the arm, you know, hold that for a little bit.
I saw 3 squats each. That might be my personal squat limit. So that's 1. I can't really go that low, but my chair's in the background.
Stretch your arms out in front of you.
Wow.
The other thing you guys should do is actually hop a little bit to get the blood flowing. Jumping jacks. Awesome. So why am I doing this? Because the more blood flows to your brain, the more of your attention I'm going to have. So it's a very sneaky way of stealing some more of your calories for the next 25 minutes for us. All right. So let's dive. And by the way, let's do some polls here. So who feels that they've learned something so far? Let's see. Again, many of you have taken classes in machine learning, so hopefully this should be a review for some of you. But I feel that, cool, there's a lot of people with strong 5s here, which is great. Cool. So yeah, we have 38, 34, 24, 30. And then how's the pace? How are we doing? Am I going too slow? Am I going too fast? All right, so somewhere between just right and slightly above that. Cool. And then lastly, how well do you feel you're following? Wonderful. No, Wilson, you're not. So yes, recitation tomorrow will be a review of all of this. This is great. Okay, awesome. So again, 82200. That's great. Cool. So let's now dive into neural networks. So again, I showed you this picture in the first slide. I think this is a great representation of what we mean by deep learning. The fact that we have networks of multiple layers, which are going to be learning abstractions of the original data. So at the bottom layer, you're going to have connections directly to your input. And then in the first layer, the first hidden layer, you're going to have information from this input layer. And that's going to be making some abstractions, for example, learning about edges. And then you're going to be making corners and contours, building on the edges. And you're going to be learning object parts, building on the corners and contours. And then you're going to be identifying objects based on their parts. Okay, so that's the hierarchy that we're going to be looking at in all of these deep learning architectures. So this has its roots back in the 60s. This is something that has been around for a long, long time. The main difference that happened in the model space itself is the concept of convolutional filters, which are learned as a separate set of parameters that will be applied throughout the image. So instead of learning what an edge is here and independently learning what an edge is there, you're learning the concept of an edge and you're applying it throughout the image. And that's what these convolutional filters are doing, okay? Today, we're not going to talk about convolutional filters. We're going to have a whole lecture on that on Tuesday. But today, we're going to be learning about the foundations of such deep neural networks without worrying about this extra set of parameters. So for now, it's going to be just weights that are going to be computed at every one of those levels, okay? And again, as I mentioned in the first lecture, These are inspired by the human brain and by information being received through the dendrites of every neuron in your brains, and then sending a signal out after you cross a particular activation threshold, and sending that signal through your axons to all of the downstream neurons. Now, you can abstract away this biological construct into a computational construct that basically says the output of this particular neuron is going to be a weighted sum of the inputs of all of the neurons that are talking to me. So I'm going to have a weight associated with each of those. And that's where the learning happens. All of the learning goes into those weights. Everything else flows just through the network. We basically have different inputs. So if I show an image of a cat or an image of a person, these are just inputs to the different pixels. What I've learned is a function that transforms these pixels into a probability of being a person and a probability of being a cat. And all of this learning function does is assign values to those internal weights. Okay, who's like 100% with me on this? Because I think this is, you know, just at the core of what a deep learning neural network is all about. Perfect, good. You guys are doing awesome with the polling, by the way. Thank you so much for all these answers. Okay, so we have 7221, 700. So this is at the network level, and this is at the level of every one of those nodes. So every one of those nodes receives inputs, scales them according to some weights, and then if they cross a threshold, it sends the exact same output down all of its descendants, down the network, okay? And what is that function that is being computed? You could compute a linear function, for example, the sum of all the x's weighted by the weights, and, you know, some bias, okay? And that should be an equal sign. And that's the original sort of neural networks. But the place where the neural networks became truly powerful is when that function was then passed through a non-linearity, okay? And that non-linearity allows you to now dramatically increase the space of functions that you can approximate. So this is what we call a neural network, which is a 4 layers deep neural network. And deep multi-layer neural network can learn almost any function as long as we introduce a very funky construct, which is a non-linearity. What is a non-linearity? A non-linearity is just something that just breaks the, you know, what I get in is what I get out, scaled by some factor. Why? Because if all you have is linearities everywhere, then it's just one big linear function and you can't really learn that much. But by introducing the non-linearities, you're allowed to suddenly learn XOR functions and, you know, all kinds of sort of logic functions and shapes and curves and, you know, all kinds of other contours and transformations that are simply not captured with purely linear networks. So the original nonlinearity was basically this sigmoid unit, which is taking the concept of a neuron not firing at all until a threshold is crossed, and then the neuron fires. So they basically said, okay, by studying neuroscience of, you know, non-human mammals, and then seeing how their neurons respond to different activation levels, they basically said, oh, wow, if I give it a bunch of activity, you know, electricity, but below a particular threshold, nothing happens. And then as I start crossing that threshold, boom, something happens and it maxes out, okay? So that's where the original sigmoid unit nonlinearity came from, by basically saying the neuron either fires at 1 or it doesn't fire at 0. And as you're crossing that threshold, the activation sort of pushes you from one to the other. And you can tune that sigmoid by making it sharper or wider according to, you know, particular parameters. You can basically say, what is the total activation level? At what point X do I cross it? And how steeply do I cross it? Okay, and these are just parameters that you can use to effectively scale that sigmoid unit. So then beyond that sigmoid unit, folks basically said, well, some neurons don't just stop at one, but sometimes they fire a lot. So then the soft plus unit was adapted to basically have, again, no output until you cross a threshold. But as you're crossing that threshold, you don't just stop at one, but you continue to the level of input that you received. So that gives you more expressivity, and that gives you the ability to sort of truly shout out, wow, it's really a cat, when you see something that sort of truly makes that neuron fire. Okay, and that's the soft plus, the soft plus or the soft max function, which is expressed here. Again, it has no saturation and a smooth transition. But in modern deep learning, we mostly ignore the soft plus and the sigmoid in favor of a much simpler function, which is basically a rectified linear unit, or a ReLU. So rectified linear unit basically means it's a linear response as long as I cross my threshold. So above a particular threshold, I just respond x equals y. And below that threshold, I simply don't respond at all. Okay? So who's with me with all of these activation units here, all of these non-linearities? Okay, very cool. So we're at 78, 13, 900. Okay, so every hidden layer basically has some activation function as its output, and we're going to be talking about input layers, output layers, and hidden layers in between. And what deep learning is about is having multiple of these hidden layers. Okay, and again, there's multiple output functions that you can have. You can have a ReLU, you can have a sigmoid, you can have a tangent, so tanh, which is basically going from -1 to +1 rather than from 0 to 1. Again, very similar to the sigmoid, but just scaled. And then you can also have a leaky ReLU, which has a strong activation before, but also some activation prior to that. And then comes the learning. Then we basically say, okay, so how do I adjust all of these weights based on the input to match the output? So I get a bunch of images of cats, I get thousands of images of cats and thousands of images of a person. And what I want is to learn the function that translates a bunch of pixels into an image of a cat or a person, or a character 3 or a character 4. So how do I learn all that? The way that I learn that is by having these output units tell me, oh, well, you were supposed to fire for cat here, but you clearly didn't fire for cat. So why don't you adjust your weights all the way down? Okay, so that's what the learning process does. It basically says, how do I adjust the weights so that I match the output function that I'm supposed to be matching? Okay, and the way to adjust the weights is through the partial derivatives of the error with respect to each of the input variables. Okay, the way to do that is to basically say, I will adjust my weight from time t-1 to time t. I will adjust my weight by taking the derivative not along all of the dimensions, but along a particular dimension. Okay, so I can basically take the derivative along this dimension for x1 and along that dimension for x2. And by taking the partial derivatives of the error with respect to each of the weights, I can basically tune my weight update to be closer to the true value by minimizing that error. So basically I'm taking the derivative of the error and then moving the weights closer to that. Okay, who's with me so far? this is basically the foundation of gradient-based learning. Okay, this is very helpful. So 39, 39, 16, 60. And then how's the pace? Am I going too fast? Am I going too slow? Am I going just right? Okay. People feel that I'm just right 41% of the time and just slightly too fast 50% of the time, but almost no one way too fast. So yeah, okay. So now we have this derivative with respect to the weight, and we can add all kinds of bells and whistles on that. In fact, let me look at the chat to see, are the TAs answering all these questions? So hey, TAs, do we have any questions that that haven't been answered so far that I should answer live?
I think one question that we haven't answered yet is an example of why you would use a soft plus. Like over something like ReLU, I think.
Yeah, so it's not really that common. It's, you know, more complicated to compute, but it makes for a smoother transition. So basically, if you're trying to do gradient descent over sharp edges, then you could run into issues here. So basically, this would make the gradient descent more smooth, and that would be one advantage of the soft plus. But in practice, it just makes computation harder. Any other questions that I can help answer? Or and at the same time, Jackie and the rest of the TAs, if there's some clarification that you feel were helpful in the chat, you're welcome to just give them here live. So you know, when I stop, we can do that. Okay, so that's this term here. So the derivative of the error with respect to each weight. But then I don't just do this at one level, I do this at every level. So if I only had one such input, that would be super easy. I would be like, okay, great, let's take the derivative that way. But then what I have is actually the derivative of this depending also on the derivative of that, which is also depending on the derivative of this, and so on and so forth. And that's what backpropagation does. It basically allows you to sort of propagate these derivatives using something known as the chain rule down the network. And what is the chain rule? The chain rule is basically allowing you to compute at every one of those levels that function as a function of this one, which itself is computed as a function of that one, which itself is computed as a function of that one. Okay, so that's what the chain rule allows you to do. It allows you to compute any one of these as functions of all of the previous layers. Okay, so that derivative is going to be taken at every one of those, but not just with respect to this, but also with respect to all of the things that feed into that in order to adjust the weights. Because if I only adjust these weights, then, you know, I don't really learn how to construct anything from the input. Basically, what I need to do is adjust the weights all the way down. And that's what all of these partial derivatives allow me to do. So if I take, you know, this derivative here, I can express that as the derivative with respect to all of these intermediate variables at every one of those layers. Okay. So, but there's a lot of additional bells and whistles that I can add to this. So basically the most foundational and basic gradient descent is simply the partial derivative of the error with respect to each weight. But then I can add a learning rate, which basically tells me, well, great, I have the direction of that derivative, but how much should I scale it? And that's where the learning rate can come in. It can basically say, well, I can learn really fast by taking bigger steps along that gradient. And that's sort of where this picture comes in. I can basically say, okay, I find that this gradient is moving that direction. Maybe I should jump way that way, or maybe I should jump just a little bit. So that's where that epsilon comes in, okay, the learning rate. And it's needed to avoid overshooting the optimal solution. But in addition to that epsilon, what we can add is a weight decay, which basically, which again, in this minus sign, it doesn't just take the gradient, but it actually subtracts the previous time step weight multiplied by some decay factor. Why is that helpful? That's helpful because that weight decay will cause very, very large weights to decay by a lot more. And therefore, it's sort of pushing your weights to be smaller and more contained. Okay, so it penalizes large weights to prevent overfitting. And then in addition to that, I can basically ask, what was the delta at the previous time step? How much did I change in the previous time step? And in what direction did I change? And based on that delta, I can include some momentum that basically makes sure that I don't jump over the correct solution back and forth, back and forth, back and forth. But if I was moving in this direction, now moving in that direction, I kind of slow down smoothly and eventually converge in the right answer. Okay. So we talked about the learning rate, we talked about the weight decay, and we also talked about the momentum based on both the magnitude and the sign of the previous update. And in multiple dimensions, that's also the direction of that previous update. Okay. And that's what gradient-based learning does. And now what stochastic gradient descent does is that it randomly samples a subset of the samples each time, and then it updates the weights using only that subset. And with online learning, you can update the gradient using only one training data point each time. As you're seeing points, you're sort of adjusting the gradient based on those points. Okay. So let's see who's with me so far. Very cool. Awesome. So 17, 12, 2, 0, 0. All right. So now let's dive into some of these methods for basically going across the multiple layers. Okay. So the derivative of z relative to some weight here is allowing us to now optimize the weight down here, which goes through multiple layers. So how do I adjust that? Well, I can take the derivative of z with respect to w, which is simply, and that's where the chain rule comes in, the derivative of z relative to y, and then the derivative of y relative to x, and the partial derivative of x relative to w, which is basically computing the same function each time, which is the derivative of that function f. Because all of my transformations have the same function, it's basically f derivative of y, f derivative of x, f derivative of w, which is, and what's y? Y is simply applying the function f twice on w. And what's x? That's applying function f once on w. And what's w? That's not applying function f at all on w. Okay, so that's where the chain rule comes in. So the backpropagation, basically what allows you to do is that you compute the gradient relative to any weight up and down the chain just by chaining down these partial derivatives. And you can basically look at particular examples of backpropagation moving through of all of these partial derivatives. So every single time I'm computing these gradients relative to all of those, okay? So I basically have a particular function that I'm computing across all of these all the way down. So we basically have the local gradient at every step, and then we have the far away gradient all the way down, okay? So this is now the, the most basic foundations for this learning. And we have the ability to go back through and train our models this way. And then, of course, the challenge is, how do we know how many parameters to have? How do we control the complexity of the model? And that's where model capacity is important to recognize. So what is model capacity? The capacity, or the VC dimension of a model, describes how many points can be correctly predicted when they're produced by an adversary. It basically tells you what is the overall modeling ability, how many, it's related to the model parameters, but it's not just the parameters. It's also like I could have a bazillion like linear parameters, But if I don't have anything quadratic, it doesn't really help me. So it's not just the parameters, it's also the types of functions that you can compute. So that's where, the VC dimension, which is basically the effective dimensionality of the model. So the capacity is a non-parametric model is defined by the size of the training set. So if I'm looking at nearest neighbors and I ask, just how do I classify a space based on nearest neighbors, then every single XY coordinate on that space will be defined by the proximity to its neighbor according to this Delaunay tessellation of the space. Now, for example, K nearest neighbor computes the output based on the K nearest training examples. Very often it is, a very good method and certainly a very good baseline to beat. But then the generalizability of a model talks about the ability to perform well on previously unseen inputs. And therefore, if you're sort of training this classifier based on all of this, you might not realize that, well, these guys were just slightly off, and future points that are in that space are most likely going to be red rather than blue. So if you train based on nearest neighbor, for example, you might have very poor generalization power because you're not really learning the function that separates these data sets. And that's where generalization truly comes in. So the generalizability of a model describes the ability to perform well on previously unseen inputs. And I previously showed you a graph like this where the x-axis were the epochs of training. But here the x-axis is the capacity of the model. So the x-axis is now basically telling you what is the effective number of parameters or the effective number of dimensions or the VC dimension of my model. And what you can see is that there's, again, with more and more and more parameters, I can match my data set in blue better and better. But my generalization error, again, increases. And again, the bias tells me how well do I match the data set that I'm given. And the variance basically tells me how well do I match the future data sets based on the variation in the stochastic samples that I obtain from the real world between my training set and my testing set. So if you have, for example, only 3 hidden neurons or 6 hidden neurons or 20 hidden neurons, then you can approximate these functions with more or less capacity. And you can reduce the capacity of your model to avoid overfitting. But then the challenge is that if you reduce capacity, you're also reducing the space of possible functions that you could approximate. So another way is to simply regularize your parameters by saying, let me penalize the magnitudes of those parameters rather than simply, avoiding having more parameters altogether. So you can trade off parameter regularization versus model complexity regularization. And a very helpful demo for you is to look at different types of points. For example, if I have very simple data, then I want to network with perhaps fewer neurons. And you can see here that I can learn this very nicely. But if I have a network with, say, 20 neurons, then it's sort of, learning perhaps a little too much. And if I have, for example, a spiral data, you can see that after a certain number of learning periods, I can sort of truly approximate it. But if I have very few neurons, I'm simply not able to do so. It just doesn't have the capacity to do so. It can't approximate a function that's sufficiently high dimensional to get at these neurons. So if I increase the number of neurons, however, I'm increasing the model capacity. And now I'm starting to learn more complex functions. But again, it's still not able to do so. And I can change the network again. And if I give it enough neurons, you can see that after a certain number of epochs, it's starting to approximate that function. Okay, so I hope you guys recognize the differences between the capacity of a model and other forms of regularization. So, and we talked last time about dropout, which is another form of regularization. We talked about clamping the model to sort of force lower dimensional representations. And there's many additional ways of doing this. You can basically have more training data. You can tune your model complexity based on the number of layers, the number of units. You can force early stopping using a validation set to choose when to stop. You can include weight decay using both L1, a linear function, and quadratic function for regularization that penalizes the sum of the absolute values of the weights or the sum of the squares of the weights. You could also add noise as a regularizer. You could basically say, instead of matching every point exactly, I'm going to move the points randomly to basically force regularization that way. So you can actually think of noise in your input as actually a regularizer. You could also have Bayesian priors on the distribution of parameters for your model. You could also think of weight decay as a Bayesian prior. That's basically telling you, I'm expecting my weights to be smaller, and therefore every single time I'm going to be decreasing the weight, moving it closer to my prior, when the evidence itself is going to be pushing it closer to the maximum likelihood estimate. The prior is going to be moving it closer and moving the posterior closer to a sort of lower weight. And we can also think about the variance of the residual errors of not just what is the error itself, but how much does the error vary accordingly. All right, so that's the end of lecture 2. Let's see, quick polls. Who's with me so far and who feels that they've sort of gotten the stuff that I was presenting? Lovely.
Notice we have 2 great questions about capacity in the chat.
Awesome. Great. So I'm going to get to them very shortly. So 2767 700. And then the next one is who feels that they've learned something. While I'm reading the questions here. Awesome. Very cool. So cool. We have 53, 40, 070. And let me get to the question. So how is the capacity of a deep neural network calculated or estimated? It really depends on the activation functions that you're using and on the total number of weights that you're using. So I don't think we want to think of capacity as a number. It's more of, I would say it's more of a concept of what is the expressivity of your network. And we can think about more capacity coming with more parameters and also more expressive functions for those parameters, and less capacity with both of these opposites. So, you know, most of the time we're not going to worry about the absolute capacity and how it's calculated, but instead am I adding capacity or removing capacity? And then to increase capacity, how does one decide when to add more units to a larger versus adding new layer? Gosh, these are such fantastic questions, and they are at the core of a lot of the architecture engineering for neural networks. So basically a lot of the deep learning field has been about the trade-off between more layers, wider layers, you know, more connections, more abstractions, more, you know, in particular architecture, we're going to talk about, you know, convolutional filters. We're going to talk about, you know, the other features of convolutional neural networks and recurrent neural network over the next 2 lectures. And that's when we're really going to get into architectures. But the quick answer is it's an art. We don't really have a theory for what is the right balance of complexity. Okay, lovely. You guys feel that you've learned stuff? Good. Awesome. Thank you, everyone. See you in recitation tomorrow at 3 and first mentoring session tomorrow at 4. So please record your videos, and I've seen a lot of videos coming in, and that's great. And watch your classmates' videos and upload your profiles. And we're going to be compiling all of that, and we're actually going to go through it in the mentoring session tomorrow to actually meet each other, because that's the whole point of having a class, because you get to have awesome teammates, which are going to be your colleagues and partners for the rest of your life. So Take a step to both introduce yourself in the most positive way to your classmates, tell us about your background, your interests, your types of projects you're interested in, kind of narrating what's going to be on your form for each person in a visual format, number one. And then number two, take the time to actually meet your classmates, read about their profiles, watch the videos for the people that are the closest to your interest, and so on and so forth. All right, see you guys over the next 2 days. Bye-bye.
Thank you.
Thank you.